All right, taking a look at chapter 4.10, antiderivatives. All right, just like every other idea in math, once we know how to do something, we look for a way to undo it. We learned addition, so we learned how to undo addition, called subtraction. We learned multiplication. How do you undo that? Division. We learned how to FOIL, all right, with algebra. Then we learned how to factor, to undo it, all right? So an antiderivative is the undo of a derivative, okay? For these ones, we usually call them kind of like capital F is the antiderivative of lowercase f. Or if you take the derivative of capital F, you should get lowercase f, okay? So we're trying to undo the rules of derivatives, all right? So in general, I will say this is kind of the main focus of Calculus 2. The next module, integration, all right, uses these antiderivatives, all right? And the antiderivative and this thing called an integral, for the, I guess, easiest way to say it, they're pretty much the same thing, all right? There's some fine details that are different, but an antiderivative and an integral that you'll soon learn are pretty much the same idea, okay? So let's see if we can do them. I want to find the function, find the capital F, whose derivative gives me 3x squared. All right, so we know the rules of derivatives, especially for these things. All right, you take the power, you move it in front, and then you take away 1. All right, so an antiderivative, if we have 3x squared, to do an antiderivative, we add 1 to the power, and then we divide by that new power. Okay, that's the general rules for antiderivatives. We learn that, so if we do this, those 3's would cancel, we'd have x to the third. All right, so x to the third is the antiderivative of 3x squared. All right, so let's try that again. If we took the derivative of this, the 3 would move to the front, so 3x, and we take away 1 from this, okay? So again, for an antiderivative, we add 1 and then divide by that new power, okay? So the power moving in front, we have to divide by it, and subtract 1 from the power, we have to add 1 to the power, okay? Now you can always double check your answers by just taking the derivative and seeing what happens. All right, well, let's try another one. All right, so we have 12x to the 5th is the answer to a derivative. So the original problem, we add 1 and then divide by that power, okay? Now this should work out. 12 divided by 6 is 2x to the 6th, okay? So let's just check, does this work? 6 times 2 is 12, x to the 5th, yeah, all right? So yes, that is the correct antiderivative of this problem, okay? All right, the derivative of something is 1 over x. Well, some of these we just know. I know the derivative of something that gives me 1 over x. The answer here is the natural log. That's just a rule. I know the derivative of the natural log is 1 over x, so the antiderivative of 1 over x has to be the natural log. All right, the derivative of something gives me cosine. Yep, I know that one. That's sine. The derivative of sine is cosine. All right, the derivative of what gives me e to the x? Well, I know that. That's e to the x. The derivative of e to the x stays the same. Okay. All right. As I was talking about, the integral is another kind of way to say and write antiderivatives. All right. This kind of wavy s, long s, is the mathematical term integral. All right. So we're going to integrate a function. The dx, all right, just means that we are integrating with respect to x. Do you remember doing like d dx, the derivative with respect to x? All right, so it's the same idea. We're going to integrate, and x is the variable we're dealing with. Now, whenever you do an integral versus an antiderivative, all right, these integrals, we just kind of put this extra little plus c at the end, okay? So the general idea is that the plus c is just some constant. It could be any number whatsoever, okay? So the general idea, like up here, we could have like a plus 4, okay? Now, we didn't have a plus 4 up here, but there could technically be a plus 4 plus some constant. Remember how we were checking these earlier? If we take the derivative, we should get back to the original, right? The derivative of e to the x is e to the x. What's the derivative of a constant? Well, it cancels out. It's 0. It's gone. All right. So there could be some number being added or subtracted at the end. I don't know about it. All right. So all I know is that the derivative is this thing. I can put any number right here, take the derivative, and it will still give me this answer. So that is what this plus c at the end of all of these integrals, all right, means. When you do an antiderivative, you don't need the plus c, all right? But when you do an integral, you do. And that's really the only difference between the two things, all right? Do you need the plus c or do you not? Okay. So again, the power rule, to do this integral, all right, of 20 x to the third, we leave the 20, we say x to the fourth, and we divide by that new power. All right, we add a plus c at the end just to say, hey, yep, this is an integral, not an antiderivative. All right, and then we reduce 20 over 4, that's 5. And again, we leave that plus c. The plus c is just a constant. Any number could be added to the end. All right, to do this one, I don't like that that's down at the bottom there. So I can make this the negative fourth power. So I leave the 12. I add 1 to negative 3. I'm sorry, to negative 4 to make negative 3. And then I divide by negative 3. All right, 12 divided by negative 3 is negative 4. Don't forget my plus c. Now I can make this look a little bit better. That negative exponent can move to the bottom. And I've got my answer. All right. So again, in general, antiderivatives and integrals, they're equivalent, just that little difference. Antiderivative means if I take the derivative, I get this thing. All right. Integral means I need what's called a family of functions. That plus c at the end means I can add whatever number I want to at the end, and it will still be the same thing. Okay. Now, we do use that plus c as we learn more and more. All right. That plus c can do what's called initial value problems, basically meaning if I know a little bit about the original function, the capital F, I might be able to, figure out what that plus c should be. What number should it be? All right. And so we kind of do some things with that as we go. All right. So let's practice a few more of these. Let's make sure we can handle some antiderivatives or integrals. All right. So again, all of these polynomials, they're just powers. So just like derivatives, you can do the derivative of each piece. Integrals, antiderivatives, you can do just the integral antiderivative of each piece as long as they're being added or subtracted. So it'd be 5x to the fourth over 4, 7x cubed over 3, 3x squared over 2, 4x to the first over 1. All right, now I should put a plus c at the end, and then look to see if anything reduces. In this one, yeah, that's it. Nothing reduces. I guess I don't really need the over 1 and x to the first power, but that's our answer. All right. Here we have 3x. I would rather see this as to the 1/2 power. So when we do our antiderivative or our integral, we add 1 to our power, and then we divide by that new power. All right, so when you divide by a fraction, I hate writing plus c until the very end. That's just my personal opinion. Instead of dividing by 3/2, I'm going to times by 2/3, same change flip. Now my 3's can cancel. So I have 2x to the 3/2 plus c. And then I could rewrite this as the square root of x cubed plus c. If we started with square roots, we should end with square roots and not these rational exponents if possible. All right, let's see. This one, you can't do quotients. All right, I'm sorry. There is no quotient rule for antiderivatives. All right, we just can't do those. Okay, we had a quotient rule for derivatives. We don't have one for integrals. All right, so the only thing we can do when the bottom is one piece, but the top is two, you can actually split this up into just two smaller pieces. Now, if the bottom is two pieces, no, you can't split that up. But if the top is two, yes, you can split that up. All right, so this is 3x. We would subtract these exponents. 1 minus 1/2 is 1/2. 3 minus 1/2 is 2.5, or 5/2. So 3x, I add 1 to this, that's 3/2 over 3/2. I add 1 to that, so that's 7/2 over 7/2. All right, from there, I do want to just reduce. I don't like to divide by 3/2, so I times by 2/3. I don't want to divide by 7/2, so I times by 2/7. My 3's cancel. All right, and I should go back to square root of x cubed. My 7's cancel, so I should go back to the square root, 2's on the bottom. That's to the 7th plus c. All right, you can verify some of these. Some of these, like I'm telling you, the integral of x e to the x is this. All right, to verify it, the idea is if I take the derivative of x e to the x minus e to the x plus c, I should get this. All right, that's how we verify. So to verify, derivative of x to the x, that's a product rule. So 1 e to the x plus x e to the x minus e to the x plus 0. These cancel, and we are left with x e to the x. Great. Right, I hope we're okay with that product rule. I know I went fast through it, but we're at the end of calculus, so we should know the product rule pretty well. All right, I told you earlier about these things called initial value problems. All right, they allow us to be more specific with our integrals, with our antiderivatives, and they allow us to find that actual value of c. Okay, so let's say I have this. Lower f is 6x squared. Find capital F. Do the antiderivative. Well, we kind of have been working on that. This would be what? Add 1 to the power, divide by that power. Great. All right, so my capital F of x, 2x cubed plus c. All right, sometimes we have the ability to make the c go away and get replaced by an actual number. And this is called an initial condition. Now, this f of 1 equals 5. Notice capital F. That means when x is 1, y is 5 in our antiderivative. So we can say 5, that's like our y, equals 2 times 1 cubed plus c. What this allows us to do is solve for that c value. 1 cubed is 1 times 2, so c is 3. So instead of 2x cubed plus c, I can say it's 2x cubed plus 3. I can find the actual value of that c, and it looks better. It's nice to know what that is, but I have to know more about my original function than usual. Okay, I actually have to know that initial value. All right, we can keep going. I've got the derivative of something is 3x to the negative second power. All right, so to find my y, I take the antiderivative or integral. 3x, I add 1 to that, and I divide by that. All right, so I can say this is what? Negative 3x to the negative first, or negative 3 over x. Now we know y of 1 equals 2. So when x is 1, y is 2. So add the 3 to the other side means c is 5. Great. All right, and these can be really, really useful for some word problems. All right, the acceleration of a baseball's height hit straight in the air is just given by negative 32 feet per second squared. Negative 32 feet per second squared is the rate of gravity here on Earth. All right, gravity is pulling everything down at a constant rate, down, so negative 32 feet per second squared. All right, that is just the gravitational constant in feet, okay, which is negative 9.8 meters per second squared, if you ever get asked about that. All right, two things are the same, just meters or feet. All right, gravity is always pulling us down just like that. That is our constant acceleration. All right, right now, you drop your pen, all right, even though it falls 2 inches to your desk, whatever it is dropping at a rate of negative 32 feet per second squared. That is just how gravity is pulling everything down on this Earth. So if that's the acceleration, well, I know that if I know velocity, I take the derivative to find acceleration. So if I know the acceleration, I can find the velocity by doing an antiderivative, an integral. Well, the integral of negative 32 dt, there's no variable there. I don't have to really do a power rule. That's just negative 32t plus c. All right, that's my antiderivative. But now I know an initial value. It says I had an initial velocity when v is 0. I'm sorry, when t is 0. Initial velocity is 100. Well, 32 times 0 is gone, so c is 100. So my initial velocity, negative 32t plus 100. That is the speed of my baseball. Okay. All right. Well, if that's the case, I can then integrate velocity to find its height. Position is the integral of velocity. Velocity is the derivative of position. So to integrate this, I have to add 1 to my exponent and then divide by that new power. 100 to the t, it will get t to the first. Technically, I could divide by 1 if I want. Don't need to. Plus c. And that's my height. Well, I now know an initial height. So my height is 8. When my time is 0. Notice I reduced that. 32 divided by 2 is 16. All right. And so what? C is 8. All right. So I now have the equation of a baseball hit straight up into the air. Okay. And it's there. It has that initial velocity of 100, initial height of 8. And I don't know if you remember seeing all these types of equations about baseballs flying in the air, so on and so forth. They always had this negative 16. I don't know if you ever wondered why. It's because we were actually being mathematically accurate all these years. Negative 32 feet per second squared for acceleration means an antiderivative of 16t for the velocity. All right. I'm sorry, negative 32t for the velocity, and negative 16t squared for our position. Okay, so all those years of seeing that negative 16 x squared or whatever it is in front of that quadratic formula you had to always do, we were actually always being very mathematically accurate, whether you knew it or not. Okay, we could graph this if we want to. Negative 16t squared plus 100t plus 8. All right. cool. So notice our initial height 8. We could find some of these important points if we wanted to. All right, so how would we be able to find this maximum height that we reach? All right, well, we can click on it in decimals, that's great. Or we could take our velocity formula. We could set our velocity equal to 0. Negative 32t equals negative 100. Negative 100 divided by negative 32. $3.125. Look at that. 3.125 for that maximum height when your derivative is equal to 0. All right, that's great. Now, our second derivative, our acceleration, was negative 16. It was a constant, negative 32. All right, so the acceleration, the second derivative, is negative. Okay, now always negative, which means this equation is always, when your second derivative is less than 0, negative, concave down. This entire function is concave down. I hope you would agree with that. Connect any 2 points anywhere you want to, and you would draw that straight line. It would be under your parabola. All right, this entire thing is concave down. The acceleration is always negative. You hit that baseball, it is always losing speed forever. Okay, losing acceleration forever, I should say. All right, it is being pulled down to the earth. It is losing acceleration constantly. Okay, so that's antiderivatives, what we can use them for, how we can do some initial value problems even. All right, and doing these, beyond these like basic ones, these are, I hope, really easy to follow along. This is kind of the introduction to Calculus 2 and Chapter 5. Chapter 5 will do a lot of these antiderivatives, and all of Calculus 2 is really geared on finding these antiderivatives as well. All right, good luck.